Hi there. So today we are going to try to understand the concept of microbial growth. So what exactly is microbial growth? Very simple. The study of how microbe grows, right? Pretty simple. So we are trying to study how do they grow. So when generally we study, we say there are four phases of growth. But let me tell you, when we tell this, we say that we are talking about how they grow in cultures, right? Now, first of all, we need to understand what exactly affects the growth of bacteria. So, the growth of any organism, as you know, is, let's say, nature and nurture. So nature means what kind of genes it has, right? Because genes give you the ability to exploit the environment, to get the nutrients from environment. Let's say a bacteria has proteins that can get the transport of glucose, right? So it can take advantage of glucose in the environment. It will be enriched in a glucose environment. So right, so genes are a major determinant, and obviously the remaining depends on the environment itself. What is the pH of the environment, right? Some bacteria, they can thrive even in well or a low pH. For example, if I were to say uh, bacteria that's very much associated with ulcers, Heliobacter pylori. Previously, we used to think that, okay, we get ulcers because of alcohol, because of other lifestyle problems. Yes, they do aggravate it, but it's the Heliobacter pylori which can even thrive in the acidic pH of the stomach. The story is a little bit more complex because it basically thrives in crevices, but yes, it can tolerate a lot of pH. Some bacteria can tolerate hundreds times the radiation dose as humans can, right? So it depends on the pH, it depends on temperature. So we all know the famous bacteria from which we have got the enzyme that allows us to polymerize DNA, right? So again, a lot depends on the temperature, depends on the pH, depends on the water availability around it. So generally when we talk about the growth of bacteria, we talk about the four phases. But obviously that is heavily impacted by nature and nurture. Now let's talk about growth phases. So there are four growth phases generally that we will be talking about. Lag phase, or let me use, yeah. So lag phase, generally first denominated by a plateau. Then we have the log phase, which is denominated by this incline. Then we have a stationary phase, again denominated by this plateau. And finally, we have a death phase, which is denominated by a decline. So what are each phases known by? Now lag phase, as you can quickly see, is kind of a flat line, right? Why is it a flat line? Because this is the time when you put the bacteria in a culture media or in an environment, and the environment is totally new. It is trying to duplicate its apparatus so that it can divide. It is trying to repair the injuries that were sustained, the damage that was done because of, let's say, a deficient environment. So that is why for the first few duration, we do not see much growth, right? The number of cells are more or less same. That is why we say it's a lag phase. Then comes the log phase when everything is set to be done and the bacteria divide rapidly. So there's rapid division, and that is why the number of cells increase exponentially, right? They increase exponentially. Might I like to add here when we say exponentially, because we know one bacteria divides into two, right? 2 into 4, right? So we can see why this is going to be exponential. Finally, we enter a stationary phase. Why do we enter a stationary phase? Because no matter how much nutrient was initially available, a lot of that was the nutrients have been used up, right? And not only the nutrients are being used up, wastes are being generated as well, right? So after a time, there won't be any net growth because the nutrients are being used up and a lot of wastes have been generated. Finally, the bacteria enters in what we call as a death phase. Now, what exactly is a death phase? Basically, because of the waste accumulation or the nutrient deficiency, we have so much damage done that even if the batch is transferred to a fresh media, they will not revive. So that's called death or senescence phase of uh, the bacterial growth. Now, the last one is kind of heavily being challenged. So, some say it is because of the programmed cell death that happens, and some say, well, it can be cultured again, it can be allowed to grow again if it were uh, transferred to a natural environment, right? So, there's a lot of debates going on around the fourth phase. So this was a more theoretical approach. Now, how do we represent this mathematically? Because we want to use this knowledge because we want to grow bacteria. Why? Because we want vaccines. We want bacteria to give us hormones like insulin, right? So we must understand the mathematics of the growth here. So uh, how do we do that? So we have the following parameters. We have n naught that tells us the number of bacteria at time is equal to 0 when our culture started. Nt gives the bacteria at time t. N is the number of generations bacteria has divided into between t is equal to 0 to time is equal to t. K is number of generations per unit time. So kind of gives us an idea of how speedily is a bacteria dividing, and G is doubling time. In what amount does Nt equals to N naught, right? Now, N, K, and G are something that we calculate, but N naught and T is something that we measure, observe, count. Now, for that, we have counters, like we spread them out on a very specially prepared counters like hemocytometers, and we literally count them under the microscope. We have another means like flow cytometry where we stain them with fluorescent dyes and we use the scattering of the light to count the number of cells that have passed through. So basically this requires measurement. Now once we have the two data, we can calculate what is n kg, because this is where we want to apply. Now let's try to understand a little bit of this. So if this is the equation, nt equals n naught times 2 to the power n, let's take log both the sides. So we can write log nt equals log n naught plus n times log 2, right? Now if we solve for n, because we are right now interested in n, number of generations the bacteria has divided between time t equals 0 and time equals t, right? So if you solve, you get log nt minus log n naught, and the log 2 value is 0.301, right? So from here you have a very viable input n, right? Now what is k? Now you can clearly see k is number of generations per unit time. So time here is t. So k equals n upon t. So we have these two parameters. Now what about g? How do we calculate doubling time? So in this case, let's try to find this out. So in this case, what would be nt equals to n naught, and the number of generations. Now to double the number of generation must be equals to 1, right? That's when it divides 1 times the one generation, it would just double, right? So if in what is t in this case? T is the doubling time equals g, right? So k equals 1 upon g, or g equals 1 upon k. I hope this makes sense, right? We now have our doubling time by this substitution.
We hope this video was helpful. To see more biology topics covered, click on our channel and don't forget to subscribe.